Hi everyone. Today we are going to be going through lesson 4.3. The topic is solving KEQ problems using ice tables. Unfortunately, I think this will be a long video. We got lots of examples to get through here. Okay, so sometimes KEQ problems only give us starting concentrations of reactants when asking to solve for KEQ or equilibrium concentrations. When that happens, we can solve these if we use the balanced equation and what's known as an ice table. An ice table is literally just a chart that we use to organize information. So the ICE stands for initial, change, and equilibrium. All right, we're going to go through this example here. H2 plus I2 is in equilibrium with 2HI. So you're given certain information here. You know that 0.5 moles of H2 and 0.5 moles of I2 are placed in a 1 liter flask. The KEQ is 54.3 at this temperature, and then it asks you to calculate the concentrations of H2, I2, and HI at equilibrium. So I'm going to rewrite the equation here. And then I'm going to draw my ice table. So I, C, E. There we go. Okay, so I've got H2 here, I2 here, and over in this area is going to be the HI. So initially, what do you have? So we're just going to read the question to find here what we have initially. So it says I've got 0.500 moles of H2. Now, if I make these into concentrations, you know what? I think I'm going to, let's do this. I think I'm going to do this. Sorry, everyone. So I'm going to do this. H2, I2, and then I've got HI. And I have to remember that there's two of those. You can use either the equation or this. It doesn't really matter, actually. So looking at the ice table here, I'm going to fill in my values then that I have. I know that I've got 0.500 moles of H2. Now, if this is concentration, molarity is equal to moles per liter. Now, they're in a 1 liter flask. So in that case, the liters will be 1, which means for this particular example, the molarity is going to be equal to the number of moles because that liters is 1 liter. So I can say that this is 0.500. I2, same thing, 0.500. And then when we start the reaction, you do not have any HI because HI is a product here, okay? Now, the change. How much are they going to change by? We don't know that, so we're going to try to solve for that. So the change here is going to be minus x. So we know that H2 is going to be decreasing. It's being consumed, so the change is going to be negative. So minus x for the I2 as well. We don't know what those values are. And then HI is going to increase by x. Oh, sorry, but not by x, by 2x. Sorry, I forgot to factor in the mole ratio there. So it's going to increase by 2x here. So then I can write my equilibrium expressions. So I can say this is going to be 0.500 minus x. This is 0.500 minus x. And this is going to be 0 plus 2x. So I'm just going to clean that up by calling it 2x. So I've got these expressions now. And so now I can use that, sorry, I'm just getting myself more space here. I can use that by putting it into the KEQ expression. So we're going to solve for x using KEQ. Now, remember, KEQ is going to be equal to the products over the reactants, right? So the concentration. So I've got HI, and then that's going to be squared because of that 2, the molar coefficient there. And I'm going to multiply that by the concentration of H2 multiplied by the concentration of I2. Now I'm just going to sub in values here. So KEQ, I know, hold on. Oh, I actually gave myself a space here. Hold on. Actually, I'm going to just do it over here. So KQ, like I said, is HI squared divided by H2 multiplied by I2. So now I'm just going to sub in my values, and the KQ is given to you in the question, so it's going to be 54.3, and that's going to be equal to, and now HI is going to be equal to 2x, so 2x squared, and then divided by, I've got 0.500 minus x multiplied by 0.500 minus x. So now I've got this, but it looks kind of ugly, right? If I go through and solve this, I'm going to get a bunch of x squares, because I'd have to FOIL out the bottom, and then the top part, of course, would be 4x squared. So I don't really want x squares. I want to get rid of those. So how would I do that? So some of you maybe will be able to look at this and figure out what we're going to do. If you can't, that's okay. We are going to take the square root of everything. So if we take the square root of everything, we've undone the squares here. Now, so 54.3, if I take the square root of that, I end up with 7.37. 2x squared, if I take the square root of it, I'm just going to end up with 2x. And then on the bottom, if you look here, I've got 0.500 minus x times 0.500 minus x. So that would be like squared. So one of them is just going to disappear here. So 0.500 minus x. So now you're going to go ahead and solve for x. So this is your algebra, so this would be like grade 9 algebra here. So what you're going to do, you're going to, sorry, you're going to take this up, right? You're going to multiply this up, and you're going to go through and you're going to solve, and you end up getting x equaling 0.393. Now, ideally, I want to make sure you pause the video and go through the algebra here. Make sure that you can get 0.393. You need that to make sure that you know how to do it. Now, if I look back, the question was asking me to calculate the concentrations at equilibrium. So I know what x is now. So now I have to apply that to the concentrations for equilibrium. So if I look here, okay, so at equilibrium then, the concentration of H2 is equal to 0.500 minus x. So 0.500 minus x is going to be equal to 0.500 minus 0.393. So it's going to be equal to 0.107. And the unit for that is molar, or moles per liter. Now I2 is exactly the same, the concentration at equilibrium. So what I'm doing right now is I'm using these, okay? So those are the equilibrium concentrations. So I2 is going to be the same. It's also 0.500 minus x, so that is also going to be 0.107 molar. Now, HI is equal to 2x. So that's going to be 2 multiplied by 0.397, and you're going to get an answer there of 0.786 molar for that. So those are the equilibrium concentrations. So those are the answers to this particular question, okay? So we use the ICE table because initially that's our I, the change, and then equilibrium. So it just keeps all the information really well organized for us. Now, we're going to do another one here. Calculate the value of KEQ for the following reaction if 1.50 moles of A and 2.50 moles of B are placed in a 1 liter of solution. So again, I've got that 1 liter. So that allows me to treat the moles as concentration. So we've got this system, it's allowed to come to equilibrium. So that means that it starts reacting, but we want to know how far in the reaction is the equilibrium, right? It tells you that the equilibrium, it gives you the equilibrium concentration of D. And you're asked now to calculate the value of KQ. So in the previous example, you were given KQ, now you're asked to find it. Okay, so I'm just gonna use the equation here, it's a little faster. So ICE Okay. There we go. Okay, so now I'm going to write down what I know here. Right away, it says calculate the value. Okay, I've got 1.50 moles of A. So initially, 1.50 moles of A. For B, I've got 2.50 moles of B. Now, it's because it's in 1 liter, these count as concentrations here. Now, initially, I'm not going to have any C and D here. Now, it says it's allowed to come to equilibrium, and we find out that the equilibrium concentration of C is 0.45 molar. So we're going to work backwards for this one. So looking at C, this is going to be the key to unlocking this problem here. C goes from 0 to 0.45. So the change here is going to be plus 0.45. Now, these changes follow the mole ratio. So if I have 0.45 here, I'm also going to have plus 0.45 for D because they're in a 1-to-1 ratio. B is also 1-to-1 ratio, so I'm going to subtract 0.45 here, and this will give me 2.05 molar for my B concentration at equilibrium. Now for A, I have to factor in the mole ratio again, so instead of subtracting 0.45, it's going to be 2 times the 0.45, so that's going to be 1.5 minus 0.9, and that's going to be 0.60 molar here. Just fill in this one. So now I've got the equilibrium concentrations. Whoops. And so now I can sub these into my KEQ. Now KEQ is going to be equal to A squared, don't forget that squared, times B. And then, oops, oh, I totally did that backwards. There we go. Okay, so we're going to have products over reactants. Oh yeah, I totally did that on purpose just to test you. So products over reactants, and then I've got A squared times B, and then I just sub in my values. So it's going to be 0.45 multiplied by 0.45 divided by 0.60 squared multiplied by 2.05, and you end up with an answer of 0.27. And remember, there are no units for KEQ, so just leave it like that, okay? Now, we have problems where the volume does not equal 1.00 liters. So when that happens, we just want to factor that in. So here's the question here. Before equilibrium is reached, a 2-liter flask contains only 0.246 moles of SO3 at 275 degrees Celsius. What is the KEQ? And it gives you the equilibrium concentration of the oxygen gas. Now, since the amount of substances present are given in moles, we're going to calculate the moles present at equilibrium first, then we're going to find the concentrations at the end. You can do it in the beginning if you want. It really doesn't matter. I just prefer to do it at the end. So looking at this, we've got 2 SO3 in equilibrium with oxygen gas and sulfur dioxide here. So if we look at this, ice. Okay. So initially it tells me that I've got 0.246 moles of SO3. So 0.246 moles. And so at this point I don't have any oxygen gas or SO2. Now the only other piece of information I'm given is that at equilibrium I know that I've got 0.042 moles of oxygen. So that tells me that the change here was 0.042. Now I'm going to follow the mole ratio here. So for the SO2, I have to take into consideration this 2. So this is going to be 0.84. So I multiplied that 0.42 by 2. And the same I have to do for the SO3, except this is a subtraction because this is being consumed. So minus 0.84. Oh, sorry, I missed a decimal. Oh, I totally missed a decimal. Yikes. Oh, man. Okay, so sorry, this is 0.042. There we go. And this is going to be minus then 0.084. So now I just subtract those numbers. I take 0.246 minus 0.084, and I get an answer here of 0.162. Now I'm asked to find the KQ, but to find KQ I need concentrations. These are not concentrations at this point, these are moles. So if I divide each of these by 2, I can calculate the equilibrium concentrations. So then this would be my equilibrium concentrations then are going to be 0.081, 0.021, and 0.042. So now I can sub these into my KQ expression, which is going to be the concentration of the oxygen gas multiplied by the SO2 squared divided by SO3 also squared. So I'm literally taking these numbers and I'm going to sub them into the values here. I'm just going to take a quick little shortcut, and I get a KQ value then of 5.6 times 10 to the negative 3. And again, no units. Now, that number is less than 1, so that tells us that this reaction didn't get very far. The equilibrium is very much closer to the reactants than it is to the products, and we learned about that in our last lesson here. Okay, so that would be how you solve those ones. So you just follow it through with the moles and then change it to concentration. Make sure you remember to do that before you put it into your KEQ expression. Okay, so another example here. We've got 1.25 moles of A, 1.50 moles of B, and then we've got a KQ expression here. So calculate the concentration of C at equilibrium. So looking at this, we're going to draw our ice table. A is 1.25, B is 1.50. I don't have any C or D, and so I'm not given any information other than this, so I have to just use X's here. So the changes are going to be negative X for A and B, positive X for C and D, and so I end up with getting 1.25 minus X, 1.50 minus X, X, and X for my equilibrium concentrations. Now, I have KQ, and I want to find the concentration of C. So this is what I'm looking for. So I need to solve for X then. So I've got a KQ expression, right? KQ is going to be equal to the products divided by the reactants. So C times D divided by A multiplied by B. Now, if I sub in my values, I've got 0.0010 is going to be equal to, and now C is X, D is X, and I'm going to, on the bottom, it's going to be a 1.25 minus X multiplied by 1.50 minus X. Now, here's where your brain should be saying, uh-oh. So you should be saying, uh-oh, because, did I put this on there? No, I don't know I did. Anyway, sorry. You should be saying uh-oh, because if you followed this through, we had a little trick in our first example where we used the square root. We can't do the square root this time method because these two terms are not the same, so we can't do that. So if we follow the math through on this, we'll end up with squares, which we really don't want. We are lazy chemists. We are not mathematicians. Well, we are really, but we don't want to do all that math. So we take a look at the KEQ. Now, if the KEQ is 0.0010, which is what it was, this means that KEQ is 1 over 1,000, so it's 1/1000. Since KEQ is really small, so that's a tiny number. That means we can ignore the change in reactants as it will be very tiny. So what that means is these here, so these two values here, because that X is so small, compared to the 1.25 and the 1.5. That means that we can actually just ignore it. So this means our KEQ expression is now going to become, I've still got x times x on the top. And I've got on the bottom now, though, I've got 1.25 multiplied by 1.50. KEQ I know actually is 0.0010. And so x squared divided by 1.88. So I can just clean that up, take the square root of x then to solve, and x is going to be equal to 0.043. So therefore, the concentration of C then at equilibrium, if we look, that's what I'm looking for. The concentration of C at equilibrium is going to be 0.043 molar. Now, you have to check your work though. Was your assumption good? So that was a pretty significant assumption we made there. So was it good? To check your work, the concentration of the reactants we used, so 1.25 and 1.50, must be within 5% of the calculated equilibrium values, so 1.21 and 1.46. So if they are, our estimate is good. And they are. So if hold on one second. Yeah, so if we look, we've got 1.25 multiplied by 0.05, so that's our 5%. If we do that, we get 0.0625, so 1.25 subtract 0.0625 is equal to 1.19. And so is it good? We had said 1.21, so yes it is. And we can do the same thing with our 1.50. If we multiply it by 0.05, we get an answer of, I'm just looking at my math here. Maybe I didn't work this one out. No, I didn't. 1, so 1.5 times 0.05, and I get 0.075. So then 1.50 minus 0.075 is 1.425. And it's within the range too, so that tells me that my data is good. Now, I'm showing you this. I'm not going to actually ask you to do this, but I just want you to know that this is how you would determine that your stuff is good. Okay. If in our example, the KEQ is equal to 0.100, so instead of 0.01 or 0.001, if it's equal to 0.1, this is only one, hold on one second. That's a typo. 1/10, not 1/100th. So this is only 1/10, which is not very small. So if we were to do the exact same thing, but the KEQ was 0.1, that KEQ is too big, so we cannot make that assumption. We cannot assume that X is small. Oh, I should actually put this in here. When you do this, you need to actually say, since KEQ is small, we will assume X is small. Okay, so make sure you put that into your problems. That would just be correct problem solving. Anytime you would do something like that in math, you would have to make sure people would able to follow it, so you want to state that clearly. Anyways, okay, so in this case, it's not small, okay? So now we have a problem. Our KEQ then is going to be equal to, sorry, I should just put the value in. So now we're going to have 0.100 is going to be equal to x times x, and then that's going to be 1.25 minus x multiplied by 1.50 minus x. So here we cannot assume that x is small. So now we have multiple x squares and we have x's to deal with. So what are we going to use? Brace yourself, the quadratic formula is upon us. So at some point in your math career, you will have seen the quadratic formula, and we are going to use it to solve this. So if you forget the quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So you're going to have to first simplify your polynomial here. So you're going to do the math on this, which people get confused of. So really try to work through this properly. You're going to work through it, solve your equation, get it into the format of something x squared plus something x and then plus your constant, right? So get it into that formula, and then you can use the quadratic formula to solve for x. Now, one of your answers won't make sense because you've got this plus or minus here, so you're going to get two values for x. One of them will not make sense, so one of them will likely be a negative number, or it just wouldn't work out the math. So you're going to throw that one away, and you're going to use the other one. I'm going to let you do that. Really try to figure this out, and when you're done, these will be your concentrations using the quadratic formula. Now, technically, you can Google, they have quadratic formula solvers online, so you can avoid all that beautiful math, but I'd like you to try it on your own. Just make sure that you can do it, okay? Okay, now, assignment. Questions, and more questions. There are a lot of questions here, a lot of examples. I have worked out answer keys for you to take a look at. You do not need to do every question, but you do want to do a fair sampling of them, right? Make sure you are aware of what's being thrown at you here. Okay, that should be it for this lesson. Thanks, everyone.